We live in a three-dimensional world, a universe defined by length, width, and height. But what if these dimensions are only a fraction of the reality that surrounds us? Modern physics suggests that the universe may contain additional dimensions hidden from our perception, shaping the very fabric of space, time, and matter. From string theory to hyperspace, these extra dimensions could explain the deepest mysteries of the cosmos, from the unification of forces to the true nature of black holes and quantum entanglement. Exploring reality beyond the third dimension is not just an intellectual curiosity. It may redefine our understanding of existence itself. The idea of higher dimensions has fascinated physicists for over a century, yet it remains one of the most profound and challenging concepts in modern science. Our everyday experience is limited to three spatial dimensions: width and height, and a single temporal dimension we perceive as time. We navigate the world, build structures, and interact with objects entirely within this familiar framework. However, the mathematics of the universe allows, and in fact sometimes demands, the existence of dimensions beyond these four. String theory, one of the leading candidates for a unified theory of physics, posits that the fundamental constituents of matter are not point-like particles, but tiny vibrating strings. The vibrational patterns of these strings give rise to the properties of particles, such as mass, charge, and spin. Crucially, these vibrations can only occur in higher dimensional spaces, typically requiring 10 or 11 total dimensions for the mathematics to be consistent. The extra dimensions are not merely abstract, they have tangible implications for the structure of reality, potentially influencing the forces of nature and the behavior of matter at the smallest scales. To understand why higher dimensions are proposed, one must consider the challenge of unifying the fundamental forces of nature. In our familiar four-dimensional space-time, gravity, electromagnetism, and the nuclear force, both strong and weak, operate under different rules and cannot be reconciled neatly. Gravity, described by Einstein's general relativity, curves space-time and acts over large scales, while quantum mechanics governs the microscopic world with probabilistic laws that seem incompatible with the smooth continuum of relativity. By introducing additional dimensions, string theory provides the mathematical flexibility needed to reconcile these forces. In higher dimensional space, the interactions of strings can naturally produce the four fundamental forces we observe, while also allowing for phenomena that cannot occur in three dimensions alone. These hidden dimensions may be compactified, curled up so tightly that they are imperceptible to our senses and even to current experimental detection, yet their influence permeates the universe, guiding the behavior of particles and the evolution of cosmic structures. The concept of extra dimensions also provides a framework for understanding phenomena that have puzzled physicists for decades. For example, the hierarchy problem in physics asks why gravity is so weak compared to the other fundamental forces. If our three-dimensional perception is a slice of a higher dimensional reality, gravity could be leaking into these unseen dimensions, effectively diluting its apparent strength in our observable universe. Similarly, the apparent mysteries of quantum mechanics, the strange behaviors of entanglement, superposition, and tunneling may be shadows of processes occurring in dimensions beyond our perception. Particles might interact or communicate through these hidden spaces in ways that seem inexplicable when confined to three dimensions, suggesting that the oddities of quantum physics are not violations of logic, but glimpses into a richer, multidimensional reality. Visualizing higher dimensions is inherently difficult because human intuition is rooted in three-dimensional experience. Yet mathematicians and physicists employ analogies to build conceptual bridges. A two-dimensional being living on a flat surface would perceive the world only in length and width, unable to comprehend height. To that being, a three-dimensional object passing through its plane would appear as a series of changing two-dimensional cross-sections, seemingly appearing and disappearing mysteriously. Similarly, we may be limited to perceiving three spatial dimensions, while higher dimensional objects and forces move through and interact with our universe, creating effects that appear enigmatic or magical from our perspective. This analogy helps us grasp that higher dimensions are not science fiction. They are a natural extension of geometric and physical laws, only inaccessible to our senses without the aid of mathematics and advanced experimentation. The mathematical formalism of string theory and its extension, M theory, rigorously incorporates these extra dimensions. In M theory, the universe contains 11 dimensions with strings generalized into higher dimensional objects called branes. These branes can be two-dimensional membranes, three-dimensional volumes, or even higher dimensional entities, each vibrating in specific ways that produce the diversity of particles and forces we observe. The geometry of these extra dimensions, how they are curled, twisted, or connected, determines the physical constants of our universe, such as particle masses and interaction strengths. In this sense, the very laws of physics we measure are not arbitrary, but are shaped by the unseen topography of higher dimensional space. The discovery or confirmation of these dimensions would not merely add more coordinates to a map, it would fundamentally change our understanding of why the universe has the properties it does, revealing a deeper order underlying the apparent chaos of the cosmos. Experimental exploration of higher dimensions remains a formidable challenge, yet progress is being made at the cutting edge of physics. High-energy particle colliders, such as the Large Hadron Collider probe, energy scales where the influence of extra dimensions might manifest, tiny deviations in particle interactions, unexpected resonances, or the apparent loss of energy into unseen dimensions could provide indirect evidence of their existence. Similarly, cosmological observations, including the study of gravitational waves, cosmic microwave background radiation, and the distribution of dark matter, may hint at the influence of dimensions beyond the familiar four. In these endeavors, physics and mathematics converge, abstract equations guide experimental design and observation, feed back into theoretical refinement, gradually illuminating the hidden fabric of the universe. The pursuit of higher dimensions is not mere speculation. It is a disciplined exploration grounded in empirical science, seeking evidence for structures that, while invisible, govern the deepest workings of reality. The unification of gravity with quantum mechanics through higher dimensions carries profound implications. If successful, it would resolve long-standing paradoxes such as the behavior of black holes at quantum scale, the reconciliation of relativity with particle physics, and the true nature of space-time singularities. Gravity, which appears so distinct and weak in our three-dimensional perception, could be fully integrated with the quantum rules that govern matter and energy, revealing a harmonious underlying structure. The mathematical consistency provided by extra dimensions is not arbitrary, it is a necessary condition for a coherent theory that encompasses all known phenomena. By exploring these hidden spaces, physicists aim to answer questions that have eluded humanity for centuries. Why does the universe exist in the form it does, and how do the fundamental forces emerge from a deeper, more elegant framework? Moreover, the implications extend beyond particle physics into cosmology and the evolution of the universe. The geometry and topology of extra dimensions influence the formation of galaxies, the distribution of dark matter, and the accelerating expansion of the cosmos. In some models, entire universes might exist on separate branes, parallel to our own, interacting subtly or remaining isolated. Such higher dimensional perspectives offer explanations for phenomena that otherwise appear mysterious, including the nature of dark energy, the source of cosmic inflation, and the distribution of fundamental constants. The study of extra dimensions is therefore not confined to abstract mathematics. It directly informs our understanding of the cosmos, linking the infinitesimally small vibrations of strings to the grand structure of the universe itself. Ultimately, exploring higher dimensions challenges both our intellect and imagination. It asks us to expand our perception beyond the constraints of three-dimensional experience and to embrace a universe far richer and more intricate than we ever imagined. Mathematics provides the map, physics the compass, and experimentation the path forward. As we probe the unseen dimensions, we may find that reality is far more interconnected, elegant, and mysterious than our senses alone could ever reveal. In this pursuit, humanity stands at the threshold of a profound transformation in understanding, where the hidden dimension of the cosmos illuminate the underlying unity of nature, offering a glimpse into the true architecture of reality. The mysteries of dark matter and dark energy are among the most profound enigmas in modern cosmology, and higher dimensions offer a tantalizing framework to understand them. Observations of galactic rotation curves reveal that the visible matter in galaxy stars, gas, and dust accounts for only a fraction of the gravitational pull observed. This discrepancy led physicists to postulate the existence of dark matter, a form of matter that does not emit, absorb, or reflect light, yet exerts gravitational influence on cosmic structures. Similarly, the accelerated expansion of the universe suggests the presence of dark energy, an enigmatic form of energy permeating all of space, driving galaxies apart at increasing rates. The origin, composition, and behavior of these components remain largely unknown, challenging conventional three-dimensional physics. However, by considering additional spatial dimensions, physicists have discovered theoretical pathways that could explain these phenomena as natural consequences of the geometry and topology of hidden spaces. Extra dimensions may provide a mechanism through which gravity and other forces leak or interact differently than in our observable three-dimensional space. In particular, gravity could extend into higher dimensions, weakening its apparent effect in our universe and giving rise to phenomena we interpret as dark matter or dark energy. Models such as the brain world scenario propose that our observable universe exists as a three-dimensional brain embedded in a higher dimensional book. In this picture, ordinary matter and the forces of the standard model are confined to the brain, while gravity can propagate into the extra dimensions. The leakage of gravitational influence into higher dimensional space can account for the observed strength of gravity, the behavior of galaxies, and even the accelerated cosmic expansion. From this perspective, dark matter is not necessarily a new type of particle, but rather the manifestation of higher dimensional effects acting upon our three-dimensional slice of the universe. Similarly, dark energy could emerge as a geometric consequence of the curvature and dynamics of these hidden dimensions, driving the large-scale expansion of space itself. Visualizing these effects requires a conceptual leap, since we cannot directly perceive dimensions beyond our own. Imagine a two-dimensional being living on a flat sheet of paper. If a three-dimensional object passes through, the two-dimensional observer perceives only a cross-sectional slice, unable to comprehend the full structure. Similarly, we may be limited to experiencing the gravitational consequence of higher dimensional objects without directly sensing their presence. Galaxies, dark matter halos, and cosmic voids may all be influenced by mass or energy, existing in these unseen dimensions, shaping the universe in subtle but profound ways. The mathematics of general relativity and higher dimensional theories allows us to quantify these effects, predicting the gravitational pull, energy distributions, and cosmic evolution that align with astronomical observation. In this sense, the elusive nature of dark matter and dark energy may be less a failure of detection than a limitation of dimensional perspective. The influence of higher dimensions extends beyond large-scale structures to the very formation and evolution of the universe. The early universe, immediately following the Big Bang, was a hot, dense, and dynamic environment where all forces may have been unified. Higher dimensional theories suggest that the initial conditions of the cosmos were shaped not only by energy, density, and temperature, but also by the geometry of hidden dimensions. These dimensions could have determined the distribution of matter, the formation of large-scale structures, and the seeds of cosmic inflation that allowed the universe to expand rapidly. As the universe cooled and expanded, the extra dimensions may have compactified, curling up to scales far below our ability to detect directly, while leaving an imprint on the distribution of dark matter, the behavior of galaxies, and the dynamics of cosmic expansion. In this way, higher dimensions provide a framework that connects the physics of the infinitesimally small, the geometry of hidden spaces and string vibrations, to the physics of the incomprehensibly vast, the evolution of the universe itself. The theoretical implications of extra dimensions also inform experimental searches for dark matter and dark energy. High-energy particle collisions, such as those conducted in the Large Hadron Collider, can probe energy scales where the influence of additional dimensions might become apparent. Deviations from expected particle behavior, missing energy in collisions, or the production of mini black holes could signal interactions with higher dimensional space. Similarly, precision measurements of gravitational waves, cosmic microwave background radiation, and the distribution of galactic clusters can reveal subtle effects predicted by higher dimensional models. Physics provides the mathematical framework to predict these signatures, while observations offer the possibility of validation or refutation. Each experiment is a probe into a hidden layer of reality, testing whether the anomalies we attribute to dark matter and dark energy may indeed be manifestations of dimensions beyond our perception. Higher dimensions also provide insights into fundamental symmetries and conservation laws. In our observable universe, certain physical constants and interactions appear finely tuned to allow the formation of stars, galaxies, and life. Extra dimensions offer a natural explanation for these constants, as the geometry, size, and shape of hidden spaces influence particle masses, force strengths, and interaction probabilities. In some scenarios, small variations in the configuration of higher dimensions could lead to radically different physical laws, altering the balance of matter and energy and producing universes vastly different from our own. This perspective suggests that our universe is not arbitrary, but is shaped by the multidimensional structure underlying reality, with dark matter and dark energy as measurable consequences of this hidden geometry. By studying these phenomena, we gain not only practical knowledge about the cosmos, but also profound philosophical insight into the nature of existence and the conditions that make our universe possible. Quantum mechanics also hints at the presence of dimensions beyond the third. Phenomena such as entanglement, superposition, and non-local interactions challenge classical intuitions, suggesting that particles may be connected through pathways inaccessible to three-dimensional perception. Higher dimensional theories provide a framework in which these quantum effects can be understood as interactions occurring through additional spatial coordinates. Entangled particles, for instance, may be communicating or interacting via hidden dimensions, giving the appearance of instantaneous connections despite vast spatial separation. From this viewpoint, the strangeness of quantum mechanics is not a violation of causality or logic, but a reflection of our limited perspective, confined to a three-dimensional slice of a richer, multidimensional reality. Physics offers the mathematical tools to describe these processes, while experimental tests such as Bell's inequality and quantum teleportation protocols provide empirical insight into the underlying structure of space itself. The intersection of higher dimensional geometry with dark matter and dark energy also opens avenues for technological innovation. Understanding the mechanisms by which hidden dimensions influence gravity or energy distributions could lead to advanced propulsion systems, energy generation methods, or novel materials engineered at fundamental scales. While these applications remain speculative, they demonstrate that the study of extra dimensions is not merely a theoretical pursuit. It has the potential to transform human capability, allowing civilizations to manipulate forces that currently seem beyond reach. The exploration of hidden dimensions becomes both a scientific quest and a practical investment in the future, linking curiosity-driven physics with the long-term expansion of human knowledge and capability. Ultimately, the study of extra dimensions, dark matter, and dark energy reveal a universe far richer and more intricate than our immediate perceptions suggest. What we observe in three dimensions may be only a shadow of a higher dimensional reality, with forces, interactions, and structures shaped by unseen spaces. By combining theoretical physics, experimental observation, and mathematical rigor, scientists are beginning to unravel these hidden layers, seeking a unified understanding of the cosmos that connects the tiniest strings to the grandest galactic formations. The pursuit of higher dimensions challenges our intuition, expands our imagination, and invites us to consider a reality in which the universe is not limited to the familiar three dimensions, but is a vast, multidimensional tapestry full of mysteries waiting to be discovered, understood, and ultimately harnessed. The concept of hyperspace travel has long captured the imagination of scientists and storytellers alike, yet it is rooted in rigorous physical theory and mathematics. In our three-dimensional experience, traversing vast cosmic distances is limited by the speed of light, a fundamental barrier imposed by Einstein's relativity. Even the nearest stars lie light years away, rendering conventional space travel across galaxies practically impossible within a human lifetime. However, the existence of higher dimensions opens new theoretical possibilities. If additional spatial dimensions exist beyond our perceptible three, then shortcuts through these hidden spaces could dramatically reduce travel time. Wormholes, for example, are solutions to Einstein's field equations that describe tunnels connecting distant regions of space-time. While traversable wormholes remain hypothetical, they illustrate how physics, combined with higher dimensional geometry, allows for the possibility of rapid movement across seemingly insurmountable distances. In a higher dimensional context, hyperspace travel is not mere science fiction. It becomes a question of geometry, energy, and the manipulation of space-time itself. Visualizing hyperspace travel requires thinking beyond conventional notions of distance. Imagine a two-dimensional being on a sheet of paper. To move from one point to another, it must traverse the intervening space. Now, consider a third dimension. The being could jump directly through a fold in the sheet, shortening the journey instantaneously. In our universe, hidden dimensions may act similarly, providing routes that bypass the ordinary spatial distances. A spacecraft utilizing such a hyperspace path would navigate not through the visible three-dimensional space, but through higher dimensional corridors, emerging at its destination far sooner than would otherwise be possible. The mathematics of general relativity and higher dimensional theories provide frameworks for calculating the energy requirements, stability, and potential hazards of these hypothetical shortcuts. While the technology to create or stabilize such pathways is far beyond current capability, the theoretical groundwork demonstrates that the universe may offer mechanisms for travel that defy our intuitive understanding of space. The theoretical implications of hyperspace extend to time and causality. Traveling through higher dimensional shortcuts could allow not only rapid spatial movement, but also interactions with temporal dimensions in novel ways. General relativity permits time dilation and curvature effects near massive objects, suggesting that manipulating space-time could alter the passage of time relative to distant observers. In a controlled hyperspace journey, relativistic effects might enable missions that span vast distances, while only decades pass for the travelers, even as centuries elapse elsewhere in the cosmos. Such considerations are not mere speculation. They follow directly from the equation of physics, showing that higher dimensions provide both a spatial and temporal framework for redefining what is possible. The concept of hyperspace therefore unites geometry, relativity, and high-dimensional theory into a coherent vision of interstellar travel, revealing that the cosmos may harbor routes beyond our conventional perception. Understanding the physics of higher dimensional travel also requires grappling with the immense energy demands involved. Manipulating space-time, stabilizing wormholes, or accessing hyperspace corridors would require energy densities far beyond current technological capability. Exotic matter with negative energy density is theorized as one possible requirement to keep a wormhole open, preventing it from collapsing under its own gravitational pull. The study of such materials lies at the frontier of quantum field theory and high-energy physics, exploring phenomena that challenge our understanding of the vacuum and the limits of matter. Even if practical implementation is centuries away, investigating these possibilities sharpens our understanding of the laws governing energy, matter, and geometry, demonstrates that the universe is not only vast, but structured in ways that, if harnessed correctly, could allow civilization to transcend ordinary limitations of space and time. Black holes and wormholes provide a bridge between higher dimensions and observable phenomena. In four-dimensional space-time, black holes are regions of extreme curvature where gravity prevents even light from escaping. Yet in theories with extra dimensions, black holes could have higher dimensional analogs with different properties. Some higher dimensional models predict mini black holes that might be produced in particle collisions. While others suggest that wormholes could connect distant points in space through higher dimensional corridors. The mathematics of these objects relies on solutions to Einstein's equations generalized higher dimensions, predicting how mass, curvature, and energy interact in unseen spaces. By studying these phenomena, physicists can test the implications of higher dimensions, both theoretically and potentially experimentally, linking abstract geometry with concrete observations. The interplay between hidden dimensions and extreme gravitational phenomena underscores the intimate connection between the microscopic fabric of the universe and the grand cosmic structures we observe. The role of quantum mechanics in higher dimensional physics is equally profound. Quantum fluctuations in hidden dimensions could influence particle interactions, vacuum energy, and the stability of space-time itself. These effects might manifest as subtle anomalies in particle physics experiments, cosmological observations, offering indirect evidence of additional dimensions. The behavior of particles under extreme conditions, such as near black holes or at high energies, may reveal the signatures of extra dimensions, providing a bridge between theory and empirical validation. Quantum entanglement, tunneling, and vacuum fluctuations may also hint at the multidimensional structure of reality, suggesting that information and energy can traverse pathways invisible to our three-dimensional perception. Physics, in this sense, becomes a tool to explore not just what we see, but what lies beyond, using mathematics and observation to illuminate the hidden scaffolding of the cosmos. Exploring hyperspace and higher dimensional travel reshapes our understanding of technology and engineering. Advanced propulsion systems, capable of interacting with the geometry of space-time, become conceivable within this framework. The integration of energy management, gravitational control, and quantum stabilization represents a synthesis of fundamental physics and applied technology. While the challenges are enormous, requiring control over forces, energy, and matter flow. Beyond current capabilities, the principles are not forbidden by the laws of nature. By studying the theoretical limits imposed by higher dimensions, physicists can chart the boundaries of what is physically achievable, guiding future generations of exploration. This endeavor exemplifies the fusion of imagination and rigor. The mathematics define what is possible, while engineering aspires to transform theory into reality. Finally, the philosophical implications of hyperspace and higher dimensions are profound. If the universe contains unseen dimensions that shape the cosmos, then our perception of reality is limited, and much of the universe's true structure remains hidden. The possibility of hyperspace travel challenges our notions of distance, time, and causality, suggesting that space is not a fixed stage but a dynamic, malleable medium. By contemplating these dimensions, we not only expand our scientific understanding but also broaden our perspective on existence itself. The universe, viewed through the lens of higher dimensions, is no longer a static, three-dimensional arena, but a rich, multidimensional tapestry full of pathways, connections, and possibilities waiting to be explored, understood, and ultimately navigated. Quantum phenomena have long defied classical intuition, revealing a universe far stranger than our everyday experience suggests. Entanglement, superposition, and tunneling challenge our conventional notions of space and causality, hinting at an underlying reality that may extend beyond the three dimensions we perceive. In entanglement, particles become linked in such a way that the state of one immediately influences the state of another, regardless of the distance separating them. From a three-dimensional perspective, this appears instantaneous and even paradoxical, seemingly violating the speed limit set by light. However, higher dimensional theories provide a natural framework in which these phenomena can be understood. If additional spatial dimensions exist, entangled particles may interact through pathways hidden from our perception, allowing correlations that appear non-local in three-dimensional space. The mathematics of quantum mechanics accommodates these possibilities, and experiments increasingly confirm the robustness of entanglement, suggesting that the universe may be far richer in structure than our immediate senses reveal. Superposition further exemplifies the role of higher dimensions in quantum physics. A particle in superposition simultaneously occupies multiple states until measurement collapses it into a definite outcome. This behavior, which is utterly counterintuitive in our three-dimensional view, may be interpreted as the particle exploring alternative pathways or configurations through higher dimensional space. In such a scenario, each potential state corresponds to a different trajectory through hidden dimensions, and observation merely constrains the particle to a particular projection observable in our familiar three-dimensional slice of reality. Tunneling, wherein a particle crosses an energy barrier that would be insurmountable, according to classical physics, can similarly be understood as motion through extra-dimensional pathways, bypassing obstacles that appear absolute from a three-dimensional perspective. These insights suggest that the peculiarities of quantum mechanics are not anomalies, but shadows cast by a deeper multidimensional order, one that elegantly unifies the probabilistic nature of the microcosm with the deterministic structure of higher dimensional geometry. The study of these quantum effects has profound implications for both theory and technology. Quantum computing, for instance, relies on superposition and entanglement to process information in ways inconceivable within classical constraints. Qubits can exist in multiple states simultaneously, allowing massively parallel computation. If these processes are influenced by higher dimensional structures, then the potential power of quantum computation may be even greater than currently imagined, tapping into resources embedded in hidden dimensions. Similarly, quantum communication, based on entanglement, enables theoretically instantaneous transmission of information over vast distances, a phenomenon that challenges our classical understanding of space and causality. The interplay between quantum mechanics and higher dimensional theory thus not only deepens our comprehension of reality, but also lays the groundwork for revolutionary technologies that may redefine computation, communication, and control over physical systems. Beyond practical applications, quantum phenomena hint at a profound unity between the microscopic and macroscopic universe. Black holes, for example, exhibit both gravitational behavior explained by general relativity and quantum properties that manifest at their event horizons. Hawking radiation, predicted through the interaction of quantum fields with curved spacetime, illustrates how quantum fluctuations are influenced by gravitational geometry, and higher dimensional models further refine these predictions. In certain theories, the information paradox associated with black holes the question of whether information is lost when matter falls into singularity can be addressed by considering extra dimensions that store or transmit information beyond our perceptible universe. Similarly, the vacuum energy of quantum fields, which contributes to dark energy, may arise from higher dimensional fluctuations. These connections underscore that quantum phenomena, while subtle and often counterintuitive, are not isolated quirks. They are deeply entwined with the structure and dynamics of the universe itself, suggesting that reality is inherently multidimensional. The philosophical and existential implications of a multidimensional quantum universe are equally profound. If entangled particles interact through hidden dimensions, if superposition reflects the exploration of unseen pathways, and if tunneling leverages extra-dimensional shortcuts, then our perception of cause, effect, and locality is limited by the constraints of our three-dimensional consciousness. Reality, in this view, is far more intricate than the world we experience directly. We inhabit a projection, a three-dimensional slice of a universe that extends in ways our senses cannot detect. Understanding and accepting this broader reality challenges our intuition, but it also enriches our sense of wonder, revealing a cosmos that is not only vast and dynamic, but also layered with hidden structures that shape every interaction, every event, and every phenomenon. Higher dimensional perspectives also offer insights into the unity of physical law. The apparent randomness and strangeness of quantum mechanics may be reconciled with the deterministic nature of classical physics when viewed from a higher dimensional vantage point. Just as a two-dimensional being would misinterpret the motion of three-dimensional objects as inexplicable, our three-dimensional experience may only partially capture the full dynamics of the universe. The behavior of particles, fields, and forces may obey higher dimensional principles that manifest in subtle ways within our perceptible world. By extending our theoretical frameworks to include these dimensions, physicists can develop more comprehensive models that account for both quantum oddities and cosmological observations, bridging the divide between the very small and the very large. In doing so, we move closer to a unified understanding of nature, one in which the microcosm and macrocosm, the seen and unseen, are part of a single, coherent, multidimensional tapestry. Experimental advances continue to probe these frontiers. Precision measurements of quantum systems, studies of entanglement over increasing distances, and investigation into vacuum fluctuations all serve as windows into the potential higher dimensional structure of reality. While direct observation of extra dimensions may remain elusive, the effects they produce are measurable and testable. Each anomaly, deviation, or unexpected correlation in quantum experiments provides hints that our universe may extend far beyond the confines of three-dimensional intuition. These investigations demonstrate the higher dimensions are not simply speculative mathematics. They are predictive tools, guiding experiments and suggesting where and how new physics may emerge. The synthesis of theory and experiment thus illuminates the profound interconnectedness of all phenomena, from the vibrations of quantum fields to the vast architecture of the cosmos. Ultimately, the exploration of quantum phenomena in the context of higher dimensions transforms our understanding of reality itself. It challenges the notion that the universe is limited to what we can see, touch, or measure directly, proposing instead a cosmos layered with hidden structures, subtle interactions, and multidimensional pathways. Entanglement, superposition, and tunneling are no longer anomalies but evidence of a richer framework underlying our observable universe. By studying these phenomena, we not only unlock new technologies and scientific insights, but also expand the boundaries of human understanding, opening the mind to the possibility that reality is far more complex, beautiful, and mysterious than our three-dimensional perspective allows. A journey into these unseen dimensions invites us to reconsider the nature of existence, encouraging a vision of the universe that is as profound as it is awe-inspiring, where every quantum fluctuation and cosmic interaction is part of a multidimensional symphony orchestrated by the fundamental laws of nature. As we reflect on the reality beyond the third dimension, it becomes clear that the universe is far more intricate and extraordinary than our everyday senses can perceive. Hidden dimensions shape the forces, particles, and cosmic structures we observe, while quantum phenomena reveal glimpses of pathways and connections beyond our three-dimensional experience. From the geometry of space to the behavior of matter and energy, reality appears as a vast, multidimensional tapestry full of mysteries waiting to be explored. By embracing these ideas, we not only expand our scientific understanding, but also deepen our sense of wonder and curiosity about the cosmos. Thank you for joining this journey into the hidden dimensions of reality. Your curiosity and engagement help illuminate the universe's mysteries, and together we continue to explore the extraordinary possibilities that lie beyond what we can see.